Hello ladies and gentlemen, and welcome to the next part of this episode. This is the last slide from the previous part, just to remind you where we got to. Next we need to cover the various rules which govern how the various building blocks can be connected together to form the different nuclei. The first of these rules is regarding the type and position of the neutron bonds. Essentially what we require is that the neutron bonds are evenly spread across the nucleus, both for double and quad column elements, and that between any two columns there are both horizontal and vertical bonds. These are required to stop the neighbouring columns either hitting each other or breaking apart, since we have to remember that all of these rings are elastic structures and thus will bend and flex as they are impacted either from fields or electromagnetic waves. Lastly, we require that in the majority of cases the neutron bonds are paired together, otherwise this unpaired neutron can cause instabilities within the structure, although later in this video we will be explaining when a non-paired neutron can be used while still having a stable structure. But for now we have these four examples at the bottom here. In the left hand diagram, the neutron bonds are only holding one side of the columns together, and there are no horizontal bonds either. This allows the columns to either bend away from or towards each other, both of which would result in them breaking apart. In the next diagram across, the neutron bonds have now all been paired together. However, again, there are no horizontal bonds. Thus in this case two things could happen. Firstly, because there are no horizontal bonds, the columns can move sideways with respect to each other, which would again lead to the structure breaking apart. Secondly, all the neutron bonds are located at the bottom of the columns, and thus the two top parts are not held at a fixed distance apart. This allows them to move about independent of each other, resulting in one or both of the columns breaking apart. In the last two diagrams, all the rules have been met regarding neutron bonds, and other than that their exact location is not very important. Thus both of these structures would have the same properties, or very similar. Something that you may not have noticed as we've been going through this is the orientation of the columns. At the bottom here we show you two different examples. The one on the left starts with protons on the front of each of the columns, whilst the right hand diagram, one of the columns starts with a proton, whilst the other starts with a neutron, i.e. the right hand column of the diagram is twisted by 90 degrees compared to the left hand column. What we find is that the left hand version is that the protons between the columns end up facing each other, which does not happen in the right hand version. Thus the right hand version is more stable because it increases the distance between the protons, hence decreasing the repulsive force between them. The same thing happens in quad column nuclei, where neighbouring columns are twisted by 90 degrees compared to each other. The final rule relates to the degree of oddness of a structure. This equals the number of unpaired objects within the structure and must be equal to 1 or less for it to be stable, otherwise the thing will just break apart. So here we show you three examples. Starting on the left we have a possible structure for copper 64. However, it has 2 degrees of oddness, and thus this structure would not exist in nature. These 2 degrees of oddness come from the unpaired neutron bond, which is located at the top of the structure, and from the unpaired NPN hat, located on the top right hand column. Out of interest, you might like to know that the correct structure of copper 64 would be similar to that shown. However, the NPN hat is replaced with a PM roof, which beta positive decays to an NM roof, whilst the extra neutron that was removed from the NPN hat is paired with the single neutron bond. However, coming back to these diagrams, if we were to add an extra neutron to the copper 64 structure, pairing up the bonding neutrons and producing copper 65 as shown in the centre, then we would end up with a stable structure. This is because now only the NPN hat is odd, and thus the structure only has 1 degree of oddness to it. Lastly, it could be argued that instead of adding an extra bonding neutron to the copper 64 structure, we could add an NPN hat to the other end of the right hand column. We would point out here that if an NPN hat was added anywhere else, then it would create another degree of oddness, as it wouldn't pair up with the NPN hat already in the structure. If we were to add this NPN hat, then we would produce zinc 67, as shown on the right, which in this situation would possibly be stable from a visual inspection, as although there is only one degree of oddness, it is short of neutron bonds to overcome the instability caused by the unpaired neutron. Trying to pair up an appendage, for example an NPN hat, instead of pairing a neutron bond can lead to an unstable structure, as shown below. In this example, if we were to take copper 62 this time, shown on the left, and add an NPN hat to it to make zinc 65, then this would not be stable. The reason for this is the fact that there are insufficient neutron bonds to firstly hold the two columns together well enough. Secondly, the unpaired neutron bond does create significant stress on the structure, and thus more neutron bonds are required to hold the columns in place. Hence it is more sensible to try and convert any appendages back to boxes first and deal with what is left, which is what we've done with the third diagram from the left. This is still zinc 65, but we have now converted the two hats into a box, plus two more neutron bonds. But there is still insufficient bonding neutrons to overcome the unpaired bonding neutrons instability, leaving us with an unstable structure. This instability in the unpaired neutron can be seen, since if we take out this unpaired neutron bond from this third structure of zinc 65, then we would have a stable structure. Conversely, if we were to add one more bonding neutron in, pairing the unpaired neutron bond, then again we would end up with a stable structure. Furthermore, moving on to the right hand diagram of zinc 67, then this is a stable structure because there are now sufficient number of neutron bonds, i.e. two more than the zinc 65, to hold the two columns together and overcome the unpaired neutron's instability. Lastly, it should be pointed out that if too many bonding neutrons are added to overcome the instability of an unpaired neutron, for example if we added another two bonding neutrons to the zinc 67 structure, producing zinc 69, then it again becomes unstable. This is because the instability in the unpaired neutron inhibits the proton's ability to stabilize the neutrons. Thus, one of the neutrons will eventually beta decay, producing a proton. However, if all the neutrons were bonding neutrons, i.e. after the decay we end up with a bonding proton, then this would create proton-proton bonding. Furthermore, since it would be difficult for the proton to be ejected due to the number of other protons and neutrons it was connected to, then this would again cause the structure to break apart. Hence in these situations, three of the bonding neutrons need to be converted into a neutron hat, i.e. a neutron-neutron-neutron arrangement. This means that there would be an even number of neutron bonds, leaving the neutron hat as the only odd thing, which will then eventually beta decay to produce an odd element. This is the end of the video, but this episode does continue in the next part, so I hope that you will actually join us for that. Lastly, please note that this proposition has not yet been accepted, so don't use it to answer exam questions. However, we would like to hear your views, opinions and questions regarding it, so thank you for watching.